Dr. How do I pronounce it? Kaczmarski, sorry about that, who is going to present latest accelerator-driven experiments on deuterium fusion reactions in zirconium at low energies. Thank you very much.
Hello. Because we are running late, I will try to keep it short. And one of the reasons is because my colleagues already spoke a little bit about electron screening effect, and I just can't skip that, I guess. So this graph was already shown as a screening effect. Effectively lowers and narrows the Coulomb barrier, and it enables deuterons, in our case, to react with greater ease. Of course, we use a metallic host because it's very good, actually very good astrophysical dense plasma model, and we get the electrons we want where we want them. Of course, these are the basic parameters of the reactions, as penetration factor, cross sections, screening energy, and so on. It was already told before. So I won't focus on that. Okay, so something that wasn't shown before, I think, it was the dependence of the screening energy compared to bare nuclei and its impact on the cross sections for the DD reactions. As you can see on these graphs, the total cross sections changes significantly if we change our screening energy. Even for 200 electron volts of screening energy, the difference between bare nuclei and this 200 electron volts screening energy is several orders of magnitude. And if we increase the screening energy even more, we can even get to very, very nice values for those reactions. Of course, the goal is to increase it as much as possible. For our case, that's why we need a very good host that have a few very important properties, as good capability of binding deuterons or hydrogen in some cases for some reactions. In itself, we used for our first experiments zirconium because it's quite well-known material for us. We know it binds deuterium very well, and the stability of the binded deuterons is very high, so we can keep it for years even in the locker and use it when we need that. Yes, and what we are doing, as you can see also, the enhancement factors for the reaction is also quite high compared to bare nuclei. It's not shown in the graph, but even comparison between those two energies several orders of magnitude. And here you can see some ultra-high vacuum results for zirconium. Of course, as you can see, the screening energy for is quite high here, and as you could see in previous presentations, it differs and that's one of the problems we are facing, the well, repeatability of the experiment, and it depends on many factors such as temperature, such as, and maybe the mostly, target contamination, and that's why we have a special system for that, where we can get very good vacuum, almost 10 to minus 12 millibar. If we do all the pumping, that takes time to get into these ranges of pressure inside the chamber, but we can do that, and that allows us to prolongate our experiments to even to long periods of time. As you can see on this graph, there is a problem with the contaminations for the low energies, and that's why it doesn't fit the curve, theoretical curve. And if you see on the graph down below, you can see the target cleaned with argon, and then after several hours there are building up some layers of oxygen and carbon on the target, and we get much lower reaction rates. So this is a very important thing to estimate the screening energy to keep the target as clean as possible. Of course, there are also some interesting things if we get some contamination on the surface of our target. For example, on the graph here, you can see that Konrad already shown it, but I will repeat that after a few hours of irradiating our target, the less than monoatomic layer of contamination, such as oxygen or carbon, appear on the surface of the target, and it actually enhances our enhancement factor, as it changes the surface of the target in such a way that the electron effective mass is higher at the surface, and the reaction is enhanced. And as you can see also, after several hours, more than one monoatomic layer is built up on the target, and enhancement factor is lower than 1. We believe that this is the most importance to develop a method to quickly estimate the electron screening. Sorry, that's not me. As I said, there need to be a method developed to fastly estimate the electron screening energy for different materials. If we find a material as a good host, we just need to do that to know how reliably it can generate the energy from the fusion, from the nuclear reactions. And we made a few measurements for different energies. Of course, the lower the energy, the cross-section is much lower, and we need to prolongate the experiment. So we need to find a gold center for this method to be effective, because as you can see on the graph, the lower the energy, maybe the bigger the difference between the monitor energy of 20 kV and the energy of measurement is higher, the lower are our errors. And we made some measurements. As you can see, the errors are significantly lower, and that's we believe that's a very important thing. And for example, for 6 kV, the measurement to get a significant count sample is several days, but for 10 kV it's only a few hours. So we can measure, let's say, 2 targets in one day, and that's, I would say, quite well. But I think we should go to the middle measurement, which gives us a better result, and it's not that long. For example, we made the measurements for 4 kV, and we got 7 counts, I believe, in one day or so. And comparing to monitor, which was in 10 minutes like 10,000 counts, so that shows the difference. Maybe I'll go back here a bit. Of course, we are dealing with some issues with this method. We have some uncertainties that are quite significant. For example, current measurement, because even we are operating on around 50 microamps for this measurement, and even 1 microamp give us several electron volts difference in the value we receive. So this is one of the main problems for us right now. Okay, and maybe I will tell a little bit about our facility and our equipment, because that might be an interest of some of you. We have a linear accelerator with ECR ion source, which gives us very good energy resolution of just few electron volts, and I mean maybe 2-3 electron volts. So that's very good for our purposes. It gives excellent stability, and for now our voltage change, so the definition of our energy is from 20 kV down to few kV, maybe 5 or 4 reliably, but I will go back to the value that's written here in a minute. And we can get very high current, which we need to balance the time of our experiment, because going down to very low energies, we need to compensate it with the current. But that, of course, gives us some additional problems, like temperature on the target, because, of course, if we go, it's hard to keep the stability of the temperature and to reliable results from that. And the accelerator is built on a high voltage platform, and we have no wearing of elements outside of, for example, pumping system. Yeah, and as I said, the experimental problems we had were the problems with current measurement, the temperature control, surface contamination, because that's also one of the most important factors. And we need to establish for each of the targets loading time, because for some of them it differs. And also the target preparation would be the most important, because some of the materials bind the deuterium or hydrogens and some don't. And to measure the screening energy, we need to find a way to obtain optimal hydrogen density or deuterium density. And here is our system. This is the ion source. As I said, it's ECR, and it gives us very good parameters. It's a state-of-the-art ion source. Then we go through the beamline. First, current measurement on the Faraday cup. Then we have analyzing magnet, which also gives us the beam separation based on a charge to mass. So yeah, okay. Sorry for that. Then we have a second Faraday cup where we can measure the actual beam that we've chosen by changing the magnet settings. Then we have the lens that focuses the beam on our target. And here is our chamber. We have load lock that allows us to change very quickly our targets. It takes only about an hour to change a target, and that allows us to quite quickly measure different samples and different materials. We have all kind of diagnostics. We have residual gas analyzer for the purposes of measuring the vacuum quality. We also have electron detector, which allows us to do Auger spectroscopy, so we can reliably measure the contamination on our target. We can also heat up the target. We can work in temperature ranges from liquid nitrogen temperatures to up to 1000 Celsius degrees. And that might be useful for some of the materials. Yeah, we have also a manipulator here that allows us to position our target as well as possible. Yeah, and as I said, the vacuum system is also state-of-the-art. We have 4-stage differential pumping system that allows us, after heating up the system for 48 hours, cooling down with liquid nitrogen. We have also titanium pump, ion pump, so basically all the best things you can get to the vacuum system to get as low as possible. Also, our chamber is a mi-metal, which means that it's shielding our measurements from electromagnetic pulses or things like that. Of course, the pumps are oil-free, so we don't get any contamination with the carbon layers building up on the target. Excuse me. And we bake out the system to 150 degrees to get the best possible vacuum. That's what I already said. Okay, and now we are upgrading our system. What we believe is also one of the most important things is to get as low with the energy as possible. And with our current system, we lose a lot of beam due to going to lower energies. Our current beam current is much lower at low energies, and the energy range now will be higher from 1 kV to 26 kV, which is, I don't believe there is a system like that in the world. And we will have a better beam focus. The whole system will be put under high voltage. Now it's not. We didn't need to do that, but now it will be a necessity. And the lens, as you can see it in the chamber, will be going very close to our target compared to as you can see here, we have the lens, and it's good 40 or 50 centimeters from our target, and now it will be almost directly in front of the target, which will allow us to put the beam as close to the target and even get better currents and position our target better. We will have also additional diaphragms, so we can change the width of the beam, and the beam will be focused much better and closer to the target. And as I said, we are also working on the current measurement, because we found out that it is a very, very important factor, and even small changes give us different results. So our proposed 2-point measurement experiment is still we are still upgrading some hardware and methodology. It's still not final, but hopefully when we will enhance few things like current measurement, and the new lens will be, we believe, in January. So we will be fully operational by then. Now we are also dealing with some technical problems with the pumping system, but it should be taken care of in next few days, maybe weeks, and we will be able to stop the dead time we are in right now and start fully operation. Thank you.
Okay, thank you very much, very interesting. I have a question regarding contamination. My experience with contamination, that most of the time it happens by the beam itself, because the beam will crack the oxygen molecules, so it will produce oxide on the surface. So if you translate your sample, do you have a cleaner surface there or not?
We can use, for example, argon to clean the surface.
No, just the surface is only contaminated where the beam was. Maybe next to the beam, it's still clean. That's what I'm saying.
Well, we have the analyzing magnet with very good resolution, and we can separate only the hydrogen or the deuterium line very well. So we don't put anything from our ion source to the target. Of course, we might have some residual carbon or oxygen inside the chamber, but as I said, with a vacuum of 10 to minus 11, it's not that big problem.
I know, but you showed that there was contamination.
Yes, this was from previous experiments.
Okay.
It was 3 orders of magnitude lower pressure. Yeah.
Okay, I understand. Thank you.
Higher pressure. Yeah.
Hi, Bob Greeny, a volunteer with the Martin Fleischmann Memorial Project. So it's thank you very much, Matthias. Is it? Yeah. Again, about the contamination in LENR experiments spanning from 1990 all the way through to our most recent experiments. Almost everything it seems to produce carbon and also oxygen, so triple alpha and quad alpha. So could it be a consideration? I mean, I've identified if you've got zirconium target with deuterium, there's a good number of reactions that will produce carbon and oxygen. Could it be synthesized in experiment? Because
I don't believe so.
Okay.
We don't have such a high energy. We'll also make some experiments with
there's a guy in the States, and they could never explain when they were making military semiconductors why in their incredibly amazing vacuum systems, their pure silicon started developing carbon contamination. There was just absolutely no sign of where it came from. So I'm wondering if you're suffering the same thing. And we have seen carbon synthesis by the bucket load. And very low energies.
Yeah, I don't know if we have seen the contamination coming directly from our target. That might be a thing to...
the electron interacting with the target, producing carbon.
Yes. Transmutation. Okay. No, we don't have high enough energy to do that, but... we can of course check with the ORZE spectroscopy if you have.
Okay, again about contamination. The most difficult is to take off completely the water from the oxygen, from the stainless steel of the chamber.
Yes.
So my question is very simple. Did you observe a changing of screening potential working at liquid nitrogen temperature in respect to room temperature? Because liquid nitrogen, the water almost disappear. Water vapor, so oxygen.
Yes.
Yeah. So is the same number or change with the temperature?
As I said, we have a very sophisticated pumping system that we can also, we have a so-called cold pot that takes, this is a huge pot filled with liquid nitrogen, so it takes most of the water from the chamber and traps in the liquid nitrogen. We also have titanium pump that is spreading the titanium and binds the contamination in the chamber walls. So these are the main systems to get rid of the water.
My question more simple. Did you observe changing of screening potential working at a liquid hydrogen temperature in respect to room temperature? It's like a cross-check of some contamination problem. So I just suggest if you don't have done.
Yes, but we haven't done this yet, but I believe it would be trapping the water inside the target, right? So we would have some oxygen contamination on the surface, and it would inflict our results, of course.
Okay.
Okay, I want to comment because maybe Mateusz does not know the old work of our group, but we actually did that kind of a measurement. And when we used liquid nitrogen in the past, we did arrive at higher screening energy values. So with liquid nitrogen, it was higher.
So there is, there was a hypothesis that screening energy can be dependent on temperature of the surrounding temperature. But it is a quasi-classical approach. This is something what is based on Debye screening, and this classical approach. So we have to do here in metals with the quantum mechanical system very dense plasmas. So it means that the screening energy shouldn't be dependent on the temperature of the temperature. Okay, so this is very simple, and there is what we. No, the contamination is a completely different situation. But theoretically, screening energy shouldn't be dependent of the energy. So this, of course, from the experimental point of view, there are a lot of difficulties, of course, yeah. Okay, from experimental point of view is of course the problem that if you cool down the targets that you have some water at the surface, but if you bombard the targets, you can increase the temperature of this first system. Another point is that you have a sputtering. So the lower energy of the projectile, the sputtering is stronger and stronger. So at very low energies, you can clean your target yourself. Okay, so it's a very nice effect, and we use for our purposes. Okay.
Okay.
Okay, yes.
What should we do?
You have a pen drive or
It's already there.
application?
It's in the computer.
Okay. Wait a moment.
Okay.
Okay. Claudio.
Claudio, we have a problem.
Sorry.
That's
okay,
all right.
okay.
Okay. Here.
Okay.
Mine.
Is your
Biberian.
presentation?
Wait a minute.
Non riesco a trovare la sua presentazione.
Where is, yeah, right. Sure.
Ho detto che sta nel computer, ma non so tu dove l'abbia messa.
Non l'ha messa qui?
Non lo so.
No, se qui dovrebbe essere. Qual è?
Il titolo penso che sia Biberian.
Biberian. Dove sta il ragazzo Matteo? Matteo, dove l'hai messa? Te l'ha data lui? 30 agosto, dove sta?
Vieni qua un attimo.
Questa qui, eccola qua, dai. Biberian, qual è?
No. The
Presente.
recent presentation.
First one.
This is?
Ok.
the top one.
La prima.
Number one.
Sorry.
E l'ha fatto lui.
No,
Basta chiedergli.
Devevi fare. Te lo presento.
Dove zoom?
Questo sta qua.
Ok. qui perché? Dunque qual è il relatore?
Sta là, perché vabbè. Ma puoi farlo anche da qui, non ci dovrebbero essere problemi. Ho spento tutto quanto e funzionava prima.
Ok, condivisi schermo, qual è il suo? Biberian questo.
Sì.
Faccio un
Ok.
5.
Full screen?
Sì, sì. Ok.
Lì è
Vado?
full screen?
No.
No.
That's not full screen.
Ok, good.
Okay, good. You made it. So that's all right. So I have only 10 minutes to finish it up, so that's okay. Because I'm done. Thank you. Bye. See you. That's so good. I don't want to do that. Okay. A few months ago, Frank Gordon sent me an email saying he has found something very interesting, producing electricity without anything. So that's a dream of everybody. So he said, could you reproduce my experiment because I want to make sure it's real, so it's not a mistake somewhere. So I hesitated to do it, because I have so many other projects on the fire that I waited a few weeks, and then I realized I had everything I needed to do it. So I decided to do it. So I took what he said, he could produce directly electricity with palladium deposited on an electrode and another counter electrode with nothing, and he puts hydrogen in it, and it gets electricity. So that's really amazing, without any excitation whatsoever. So I will present you my talk today, an introduction, the experimental setup, which is quite simple, the experiment with palladium, experiment with iron, and then a conclusion. I can give you the conclusion. Someone said all models are wrong, some are useful, so that gives you an insight about models. I don't know who he was, but he was smart. So, actually, Frank Gordon worked with Harper Whitehouse on this, we call it lattice energy conversion. And he thought at the beginning he was putting americium in the chamber. And then he realized, americium is radioactive, so it creates some kind of ionization of the gas. But then he realized that there was too much electricity, too much current compared to the amount of radiation produced by americium. So they removed the americium and there was still electricity produced. So that was really a major discovery, to my understanding. So here, one of my setup. It's a 30 centimeter stainless steel tube, 35 millimeter in diameter, with a CF flange copper. I have a tube so I can introduce gas in it, vacuum first, and then put gas. And I can measure the voltage. I have one electrical feed-through to measure the voltage, and I use the external tube for the ground, and it goes by itself. Good. Experimental with palladium. So my first experiment was very simple. I had a 2 millimeter in diameter, 10 centimeter long palladium silver alloy that Stan Pons gave me. I don't know why he had that in his closet, but he gave me that. And I tried with a stainless steel tube around it. Oh my God, it goes by itself. I'm sorry, I've done something in the programming. That's okay. I put it in the tube, I sealed it, pumped it out, and nothing happened. So I said there was 0 volts, 0 current, nothing. So at this point, I deposited palladium on the palladium silver rod by electrochemistry. I had no palladium chloride, but I had palladium bromide. So I used that one instead of palladium chloride. I'm not a chemist, I'm not an electrochemist, so I'm not very good at doing these kind of things, but I managed to have some deposit. I don't know how, I cannot repeat it, but I did it. And this time, it was very interesting, because you can see the voltages, pretty high voltage. So I was measuring directly with a voltmeter, 10 megohm internal resistance, and you can measure the voltage, the current, depending on the load, and the watts. You can see the maximum is about 8.5 nanowatts. You cannot even light a LED with that, an LED with that. So, but I realized that the larger the surface, the more current I should get. So I changed the design, and I used tubes stainless steel tubes, coaxial stainless steel tubes. You can see two of them. And this is a CF63 flange. So the diameter is much larger, about 66 centimeters, more than 6 centimeters. And this time, I deposited palladium into one of the tube, and the other one was as normal as it is. And now, I also done experiments with, what is the one? I had to do this presentation very quickly because I was in vacation, and I came back from vacation. I had to go to this meeting, so anyway. It's not very clear, but I said, it's no problem, you know. When I teach, I always say to my students that I make mistakes, so I feel free after that. Now, you can see we are in the microwatt regime, so that 3 orders of magnitude higher because I have 3 orders of magnitude more surface. That's all. So it's proportional to the surface, more or less. And a lot of voltage. And this experiment was done with a silver electrode, not a stainless steel electrode. So I have to redo all these experiments because I didn't know what to do. I didn't control anything, so I was doing and doing again and again. Anyway, you can get microwatts, so it's becoming better, pretty large voltages. And when I pump out hydrogen, voltage dropped to 0. So that's very important because to show that there's no artifact due to the contact between the two cylinders. Now, if you look at the power versus resistance load, you can see there is a peak around 850 kilo ohm, and then goes down with resistance. I mean, it's not very precise because I don't have that many points. It's very preliminary, as you can see. Now, I looked at what's happening when I pump out, there's no more voltage. I put hydrogen in it. Actually, I started with deuterium. So I put deuterium in it, and you see the red curve. So the voltage goes up with time, in hours, a pretty long time, you know, and then stabilizes more or less. So then I pumped out the deuterium, I put hydrogen instead, and same behavior. I mean, not very different, but pretty much same behavior is happening. So it seems that the loading of hydrogen or deuterium in the system varies. I mean, it takes longer second time because the first time it goes very quickly. Second time it's much longer to have the hydrogen diffusing inside the layer. Then I tried to see if there was any influence of the temperature. I didn't have any good oven, so I used my kitchen oven. I mean, this is a kitchen lab, you know. So I want to take a picture. You have the picture? Okay, now I looked at the temperature. I mean, because I cannot close the door of the oven completely, I cannot go to 200 degrees as it is set, but I went to almost 85 degrees. So you can see the voltage change sign at about 70 degrees for some reason, or between 60 and 75 somewhere. So voltage change, amazing. I mean, not amazing, but so that's what it is. Anyway, that's very important. Now, because then Frank Gordon told me that some people are working with iron instead of silver, or instead of palladium, because silver is much cheaper than palladium. So I said I should try that. So I ordered some FeCl3 from the internet, but I tried it, didn't work. Couldn't do the electrolysis of this stuff. You know, it didn't work at all. So it's a mess. So I called my friend, Jacques Ruher. I said, how should I do? He said, put iron in FeCl3 and you will produce FeCl2. But as I told you, I'm not a chemist. I tried all kinds of nails and pieces of metals. I never got the FeCl2. It didn't work. So finally, I decided to do electrolysis of a stainless steel tube with 6 millimeter in diameter and a copper anode around it, and in a chloric acid. I observed, this is a drawing of the thing, you know, this is the copper, this is after use. And you don't see the stainless steel tube inside. Anyway, the maximum voltage I observed was only 13 millivolts, so probably my deposit was not good. So I was ready to finalize writing my report, my presentation for here, And then I decided maybe I should open these things to see what's happening inside. And what I found was this black powder coming out. There's plenty. The powder is magnetic, it's black. It was really hot when it came out. It was maybe 60, 70 degrees because I could hardly touch it. And I don't know what it is. Then I looked at the tube, the stainless steel tube, and there's a blow up of the end of it. It's completely etched. I mean, stainless steel is strong. I don't know. This is what happened. That was 2 days ago, so I don't have much more than that. So something happened. I don't know what it is. Stainless steel has been etched. Conclusion, I told you I was short. I'm going short. There's a new phenomenon that has been discovered. Palladium, iron, and hydrogen are the key elements, but maybe more will be found later. I don't know, we have to try other things. Electrical power varies with resistive load. Voltage varies with temperature, and seems to increase with temperature. But I couldn't go above 80 degrees, but in the future I will try to go higher temperature. The metal deposits are extremely critical, and we don't know exactly what to do, what thickness, what structure we have. I mean, there's a lot to be done on that area. And I think by increasing the surface of the electrode and putting them in series, it should be possible to light an LED forever. I mean, something like that, I hope. That would be the best. And I already bought the Tesla car, so I need to improve a little bit the resolution. I run it with this. Next time I come, I will have to recharge my car. So thank you for your attention. That was good, short. Question.
Thank you, Jean-Paul. I think this is a funny experiment, and I would like to reproduce it with your help, you know. It's strange you can get FeCl2 adding iron pieces into a FeCl3. There must be a problem with pH, or maybe you had.
But the color didn't change, so I don't know.
Anyway.
It's still brown. It's not green.
Bob Grenier, volunteer with the Martin Fleischmann Memorial Project. Great presentation. Love the results. I'd like to have an SEM of that end iron. In Russia, when they took about a pound of nickel and they degassed it and warmed it and then put fresh hydrogen in, it produced strange radiation that filled their entire lab, so they stopped working. In 2000 or 2001, Roitskev exploded some foil, and this produced some monopoles that went 0.7 meter outside of the reactor and bound themselves to iron 57 nucleus. Changing the fine constant. And so it also works with paramagnetic nuclei. So if you have your hydrogen storage isotope, it's prepared, ready to absorb the hydrogen. When that occurs, you get this flash of this cold neutrino condensates that the Russians call it. It then binds to the iron, and this collects, and then it causes electronuclear collapse. That's my hypothesis, maybe, seeing what you see.
Maybe that's the reason. I don't know. Could be.
Do you thought about it? Did you think about it? That could be a simple thermoelectric effect that you measure. So yeah, Seebeck effect. So because you have the resistance or the number of free electrons depends very strongly on the deuteron or hydrogen loading rate, and of course on the temperature as well. So this one point, and if you look for some powders, this is also a very simple effect because some metals in absorption with the hydrogen can get powders as well. So it is, and it amounts a lot of energy because it's a chemical energy that can be free there. Okay, so it is something, maybe, I don't know, but it is just...
There's no contact potential, because there is an insulator between the two, and under vacuum there's no voltage, so you need the hydrogen to have it to work.
Yeah, you have hydrogen there.
I'm sorry?
So you have loaded the hydrogen to the system or not? So this, and then you measure the voltage, and this is just electric contact between.
No, there's no contact. They are separated. The two tubes are not in contact with each other.
Yeah, but you have measured voltage between the tubes. So there's electric contact between them.
Because of voltmeter, you mean?
Yeah, of course.
Oh.
This resistance is, of course, very large, but it is nevertheless it's important because in the thermoelectric system, it's important that the electron density will be in balance.
Yeah, but contact potentials are in the millivolts, a few millivolts, not 500 millivolts. It's a lot. It's a lot more.
It depends on the hydrogen, I would say, maybe. I don't know. I'm not a specialist in the field, but
well, in vacuum, you don't have it. I need the hydrogen. Yes.
Oui, Jean-Paul, when you have this stainless steel tube, what exactly was inside? How did you prepare it? Because it showed that it was somehow melted or something like that. I mean, I don't know if it's melting or anything like that. I just want you to restate how that experiment was done and what are the key elements of it.
Okay, so I have two tubes. One is a 12 millimeter copper tube from. People use it in plumbing, the basic plumbing, you know. The other one is a basic 6 millimeter stainless steel tube, coaxial. I put cement between the two to isolate them. I dry them. When it's dry, I put them in hydrochloric acid and water, natural water, H2O, and I put an voltage between the two to deposit iron from the stainless steel tube to the copper tube. So the cathode is a copper tube. So supposedly there should be a layer of iron on top, on the surface of the copper tube inside. Then I put it in a vacuum chamber, evacuate it, dry it, there's no voltage, put hydrogen in it, and measure the voltage.
Okay, but you didn't open this. You didn't check this copper tube between the electrodeposition in acid and the vacuum pumping with hydrogen.
I just rinse it in water, that's all.
You have seen this tube in water?
Yeah, I put in clean water to just clean up the surface.
Because an obvious explanation would be that you got some arcing during the electrodeposition.
No, there was no arcing.
Okay.
The voltage was low and the current was low. I don't have the numbers here, but I can.
It's easy to get arcs in electrolytes.
Yeah, but even if it was an arc, everything was normal when I put it in the chamber. It's after that something happened. When I opened the chamber, then oxygen came in and probably reacted with the hydrogen, and
that's why
it was hot. Yes. But the amount of powder is huge.
I have a question about the pre-electrodeposition that you have done on the copper tube. Have you done any chemical etching of the copper tube ahead of the deposition?
No, it was just plain tube from the factory.
Okay.
No, I didn't clean it. I go usually from simple things to more complicated things. So next step, I will clean it. Next thing, simple. Okay, thank you.
Yes.
Oh, this one, not my pen, bigger pen.
Thank you. Perché non va? Ah, ok. Okay. What is your presentation? In the PC? Ah, okay. Okay. Sorry. No, sorry, okay. Okay.
Good morning. My name is Fabrice David. I am very happy to be here and very happy to hear the previous presentation of Jean-Paul Biberian. At the beginning of the year, I received a mail from Frank Gordon too, and of course, I want to reproduce his result. Many time ago, we have the idea to produce directly electricity with aligner device because calorimetry is very useful. Many experiments about calorimetry were truly a masterpiece of technology and science, but it's very difficult to do. And during the last 30 years, calorimetry experiment failed to convince the mainstream. And my friend John Giles says that hot water is very good for doing tea, but totally useless as an industrial product. I am looking for the way to get the next slide. Avec les flèches? Perfect. This is the plan of my presentation. First, I will rapidly tell you about what is a fusion diode. Then I will speak about the entainment effect, which is very close to the Frank Gordon and Biberian effect. I will also speak about the result of Frank Gordon at Innoval Inc. My replication of Innoval Inc. result, and I will discuss the fact, and I will present you an hypothesis and try to make a conclusion about the result. Well, Fleischmann and Pons became make all their work with calorimetry. Long time ago, I think about a device that I call a fusion diode in order to make directly electricity from fusion reaction, cold fusion reaction or LNR reaction. What is the principle of fusion diode? If there is LNR inside a cathode or inside a device, there is production of energy at the beginning in the mega electron volt range, for example, 24 mega electron volt for the fusion of 2 deuterium, and after that there is down conversion. Down conversion was theorized by Peter Goldstein of MIT, and the down conversion ends in the thermal energy range. But before going to the thermal energy range, down conversion brings the NR energy into the electron volt range, and in this range of energy there is a lot of things to do. For example, it is possible to keep this energy to promote electron inside the semiconductor metal junction. What is a semiconductor metal junction? It is a diode, and it's possible, theoretically, to make electricity. It is possible to do fusion diode with a part of palladium deuterium alloy on a semiconductor and to get electricity. And it works. its work. It's like a solar cell. What is a solar cell? It is a diode, a planar diode. There is two semiconductors. There is light energy in the range of the electron volt. There is splitting, promotion of electron into higher energy level, and formation of electron and hole, and it is possible to get voltage, current, so energy in the external circuit. It is possible to do this thing with beta ray. It's the specialty of our friend George Miley of the University of Indiana. I take this picture 10 years ago at Nashville during an IIA meeting, but it's work. It's work. It is also possible to make energy with ion beam, electron beam, directly on a diode. Of course, the main technical problem is that the diode is quickly destroyed by the beta ray, but there is a technological solution for this problem. For example, liquid cathode. This is the drawing of my first patent. I think I wanted to use silicon wafer with palladium film on. This is the first diode, first fusion diode with part of silicon wafer and palladium deposited on by electrodeposition. This is the picture. This is the experimental device with a scintillator. With this diode, I did not record voltage, but some particle. But I never published because I was not sure that it was neutron or other particle. It is another model of fusion diode. It is our lab in Scotland. It is another better embodiment of the process with powder. I don't come in the detail, but with this diode made with a contact of palladium powder and semiconductor, it is possible to record voltage when after filling of the diode with hydrogen and after filling of the diode with deuterium. This is the record. It is the voltage with deuterium, 0.5 volt. It's not nothing. The voltage with hydrogen, and here it's the voltage with a dummy diode with argon. And Jean-Paul Biberian, 10 years ago, tested one of our diodes in his lab at the University of Lumini. There is a quick decrease, but it seems that the voltage stabilized during some day. And to be sure that it is really nuclear energy or not a parasitic chemical energy, we made other model of fusion diode. Other model. This is an oven made specially to seal the diode. This is the filling station. Another filling station in Scotland. This is the filling station near Paris, in my previous lab. This is the way to produce another model of fusion diode. What is it? It's aluminum foil, semiconducting ink from Sigma, and this silver foil is palladium foil. Palladium foil, not palladium foil from chemical supplier of palladium foil made for decoration in the for the oligarchs. They like to an emir in Paris. They like to have walls covered with palladium, and it is really palladium. It is really palladium, but very it's relatively cheap to buy. But I made a glass tube, and it is possible to enter the diode into the glass tube, to seal this part, and to to make vacuum and to put hydrogen or deuterium inside, and there is two connections. At this time, a team led by Charles Untitled in Florida read the patent and want to reproduce the result. Charles Untitled is a member of the Untitled family. It is a very famous name in the US. They produce industrial bread, donuts for McDonald's. The family owned more than 300 industrial bakery. And he had found a company in Sarasota, in Florida, a company called the BioSearch BioLife, and they do research on new pharmaceutics and also in cold fusion, research in cold fusion. They do a very tremendous work. They test more than 1,500 couple of photodiode with metal, with semiconductor, with insulator, and they observe positive results. They also do calorimetry. This is their calorimetric lab with homemade calorimeter and the fusion diode inside. A vacuum, homemade vacuum tank. I am at Sarasota in Florida doing diodes, compressing fusion diodes. They also produce a very interesting device. It is a wafer, silicon wafer, with in one side a deposit of gold and the other side deposit of palladium, and it's possible to record spontaneous voltage. Some experiment, but they use semiconductor powder and more and more resistance powder, and they observe a very strange thing, even with perfect insulator at the place of the semiconductor, like asbestos, paper, glass fabric. They observe a voltage. And at this time, I don't believe them. And now, I admit that because I don't believe them, because I feel an experimental error. I am an independent researcher. But I try to do good science. I don't want to make science fair science. And I don't believe this effect. Unfortunately, this ended our collaboration. But I admit my mistake. I was wrong. Errare humanum est, perseverare diabolicum. And this effect exists actually. And they do a lot of work, and they build a cloud chamber with a laser, a beautiful cloud chamber with a green laser, and they observe very energetic particle coming from here. It's a fusion diode, and they observe very energetic particle, but very rare energetic particle. So I don't want to speak about the energetic particle today. it is not possible that this energy will be was produced by this energetic particle. There is clearly an ionization inside the cell of Entenmann, Gordon, our friend Biberian. But the question is, what produces this ionization? First of all, this effect, I think that these effects need to be called the Entenmann effect due to the huge work made in Florida by this team. In von Gorgon, with this device, observe also a voltage and a current, because he used voltmeter of the classical voltmeter, and a voltmeter is not, even it is an electronic voltmeter, it is not the, you remember in the past we were used to use what we call electronic voltmeter. It was really electronic voltmeter with an electrometer tube. But with this type of voltmeter, there is a leak, and there is an impedance, and a lot of voltmeter have 10 mega ohm internal impedance. So if we record a voltage, there is also a current, and in the previous, the great previous presentation of Jean-Paul, we know that it is possible to get 70 microwatt. 70 microwatt is not. It is possible to run a wristwatch with this energy, to run a lamp for emergency, to run a lot of little electronic device of our time. Of course, it's not possible to feed a Tesla, but it is only the beginning. So I try to confirm, to reproduce the result. I built 3 devices. First, a device totally sealed in glass with a cylinder of steel, polished cylinder of steel, a little wire of palladium covered by electrodeposition with nanometric palladium. And it is possible to seal, to vacuum the hole, and to seal, to put hydrogen inside and to seal the device. And I observe, it is a device, it's totally in glass. And I see a spontaneous voltage of about 10 millivolt. So it is a reproduction of the result of from Gordon. I made also a glass container with inside a metal electrode. It's a copper disc, nanoparticular palladium made by electrodeposition. So it's a palladium hydride, a nanoparticular palladium hydride. It is a mesh of steel, a resin seal, and a tube for the vacuuming and to put hydrogen inside. And with this device, I observe also a tension, voltage, and I made also a dummy device with a bronze mesh and an electrode of spongious lead. Because I remember I have read in a book of Sylvanus P. Thompson, wrote in the beginning of the last century that it is possible to do some kind of photoelectric result with spongeous lead in hydrogen, but I don't succeed in I lose this book. Oh, excuse me. I will. So, are you sure? So, excuse me. So there is, with no doubt, ion inside our device. In my mind, it is not possible to explain the result with ionization by high energy particle, because it needs a lot of radioactivity. It needs, for example, we need a layer of polonium on the diode. It's not possible. I am still alive. Frank Gordon is still alive. It's not possible. In my mind, there is LNR energy. The LNR energy is transmitted to absorb hydrogen. There is ionization. The electron goes to the external circuit, and this ion diffuse in the gaseous way. This ion take electron, and it transforms itself into hydrogen, and there is cycle. There is a cycle inside, and there is production of energy. Of course, the next step will be to make this experiment perfectly sealed in glass in order to be sure that it is possible to sustain this energy during weeks, during months, during years. If the energy lasts one day, it is probably a parasitic chemical reaction, but if it lasts a year, no doubt, it will be nuclear reaction, an LNR reaction, and it will be possible to build factory sealed which was other thing like that. Thank you for your attention.
Only one moment. Only one question, very quickly, and a flash for you, a flash for him.
Just a remark, David. In the metal hydrogen field, it's extremely known that at 1 bar pressure in room temperature, when you expose palladium to hydrogen, to molecular hydrogen, you reach a level of 0.7 of hydrogen within your palladium spontaneously with no input whatsoever. This is just a reminder.
Yes. There is the palladium enters spontaneously in the hydrogen enters spontaneously in palladium, and it could become, for example, atomic hydrogen, but atomic hydrogen is not. But atomic hydrogen is not. We have succeeded to demonstrate that palladium cathode produce atomic hydrogen, but atomic hydrogen is not charged. It's not an ion, so it don't. It have nothing to do with this observation. So for me, it's a very good news, and particularly the replication of Jean-Paul Biberian. Thank you for your attention.
Advice. The lunch is in the same place where we have the breakfast, and this evening 10 people, 2 cars, can visit Torchiagina. If you want, you can write here at a quarter. Torchiagina is faccio vedere. Interrompi condivisione. Mannaggia. Dove sta? Dove sta? Okay, this is a place at 20:45 in the hall, 10 this evening, at 10 tomorrow. We have a visit. Who wants to come with me? 2 cars. One is mine, for example, another people with car. This evening is group, and you must write here. 10, 12 people. Another group tomorrow evening, okay? But I must know, because the people that wait us want to know if we go or not to go. This evening is sure that because I go, I'm going. Tomorrow in the afternoon, say me if you want to be free and visit Assisi how you wish, no? Because it's easy. Or if you want, if you have a car, I can at 2:30, 14:30, I can show Eremo delle Carceri. It's 10 kilometers from here. And I must know if some people want to go with me. Right here, during the lunch, if you want to visit Eremo delle Carceri tomorrow morning, tomorrow afternoon, we are free. And if you want to meet to speak problems, you're free. If you want to visit Assisi alone, you are free. If you want to visit Eremo delle Carceri with me, say me, wrote, and tomorrow afternoon I bring you. If you have a car, it's better, because some cars, some people that we can go, okay? Now, very quickly, in the underground, okay? For the lunch, thanks. At 2:30 here for the session, the afternoon session.
What is happening at 2:30? Going to this? It's Tuesday. 2:30, group photograph.
Tomorrow?
Yes.
Beh, tomorrow. Vabbè, facciamo la foto e poi andiamo. Chi c'ha la macchina e vuole venire lo porto lì. Qualcuno lo porto io. Ok? Ok, Gina?
Yeah, we will think about this during the lunch, but probably we will be